Assalamu alaikum. Welcome, dear students, to our second part in chapter 17 in Newton's laws. By the end of this video, you will be able to state and apply Newton's first law of motion, the principle of inertia. Let's start by reviewing together the objectives of the previous video. We have studied that inertia is the tendency of an object to resist any change in its movement. Mass is the measure of inertia, and objects tend to keep doing what they were initially doing unless subjected to unbalanced forces. If the objects are initially at rest, they tend to stay at rest, and if they are initially in motion, they tend to continue moving in a uniform rectilinear motion. Then, as we've mentioned in the previous video, Newton's laws of motion are Newton's first law, or the principle of inertia, Newton's second law, or the fundamental principle of dynamics, Newton's third law, or the principle of interaction. In this video, we will state and apply Newton's first law of motion. After we have studied the concept of inertia, let's perform the following experimental study which helps us in stating Newton's first law. We will use the air table in our experiment. Here we have a puck placed on the air table which is kept horizontal. So what are the forces acting on the puck in this case? Yes, the forces are simply the weight W applied vertically downward and the normal reaction of the support applied vertically upward. Then these two forces acting on the puck are opposite to each other, and since the puck is at rest, then neither the weight nor the normal will overcome the other force. Otherwise, the puck will go up if the normal overcomes the weight, or it will go down if the weight overcomes the normal reaction. Consequently, these two forces must balance each other. That is, they have the same magnitudes and opposite directions. So we obtain the following vector relation. W vector is equal to minus n vector, and therefore their vector sum is equal to 0. Which means that in this situation, the sum of the external forces acting on the puck is 0, and in this case, the puck which is initially at rest remains at rest. Now we will set the puck in motion on the horizontal air table. First, let's study the type of motion of the puck in this situation. We noted that the puck's trajectory is a straight line and the distance traveled during equal time intervals are equal. So the puck is moving in a uniform rectilinear motion. But what are the forces that act on the puck during its motion? Actually, while moving, the puck is still subjected to the same forces, the weight and the normal reaction of the air table. Do we have any other force? Of course not. That's because, as we've studied before, there is no friction along the air table. And we do not consider the force which was responsible to set the puck in motion because it is only found at the moment of launching of the puck. Then we only have these two forces. Consequently, again, the sum of these two forces as vector is in its horizontal motion is equal to 0. And yet our system moves even if the resultant of the forces acting on it is null. So we can draw out the following conclusion. When the vector sum of the forces acting on an object is null, then we have two cases. Either if the system is initially in motion, it keeps moving with a constant velocity in a uniform rectilinear motion, or if it is initially at rest, it remains at rest where its velocity is equal to 0. Then Newton's first law, or the principle of inertia, states that if the forces acting on a system are balanced, in other words, the resultant is equal to 0, then the object which is initially at rest remains at rest, and the object initially in motion continues with a constant velocity in a uniform rectilinear motion. Again, the converse is true. If a system is at rest or moving with a constant velocity, then the resultant of the external forces acting on it is null. So it is equivalent to say that if the vector sum of the external forces exerted on a system is 0, then the velocity vector is constant. Let's go back to the questions asked in the previous video. We can now find out the answers of these questions. So, do you think that without a force there is no movement? No, that's not true. Actually, without a force there is no change in the state of movement. Also, do we have acceleration, deceleration, deformation, start or stop of motion without a force? Of course not. We always need a force to change the state of movement of an object. And finally, can we find a body in motion when it is not subjected to any force? Yes, since we have seen that in the case of balanced forces whose vector sum is equal to 0, the object can be moving but in a uniform rectilinear motion. Let's practice now by solving the following application. Don't forget to pause the video and try to solve the applications by yourself. In the first application, you are asked to specify whether each of the following cases is in agreement with Newton's first law or not. In the first case, we have a car. The forces or the external forces acting on the car are the normal reaction, the weight, the traction force F, and the friction force. From the figure, the forces acting on the car are not balanced. You can note that F and F are of different magnitudes, then they are not balanced, whereas W and N are of the same magnitude, so they balance each other. Then the sum of the external forces acting on the car is different than 0, and in this case, the motion of the car is not in agreement with Newton's first law of motion. In the second case, a skier moves on an inclined plane as shown in the figure. Note that the screenshots are taken after equal intervals of time. If we measure using a ruler the distance traveled during equal time intervals, we notice that they are equal and the skier moves along a straight trajectory. Then we notice that the movement of the skier is in uniform rectilinear motion, and thus the resultant force is equal to 0. So the skier's motion is in agreement with Newton's first law of motion. Now we have a car moving through a bend on a road with a constant speed. In this case, the trajectory of the car's motion is not rectilinear, so there is a force responsible for changing the direction of motion. Then, the sum of the external forces acting on the car is different than 0, and in this case, the movement of the car is not in agreement with Newton's first law of motion. Let's consider our last case, which is a parachutist moving downward. In this case, the two forces acting on the parachutist are the weight and the air resistance, which are opposite, having the same magnitudes, as we can see from the figure. Then the sum of the external forces is equal to 0, and in this case, the motion of the parachutist is in agreement with Newton's first law of motion. Now let's move to application 2. A bus of mass m equal to 1000 kg moves on a straight track with a constant speed v equal 54 km per hour under the action of the traction force F. The force of friction which opposes the motion of the bus is assumed to be constant of magnitude F equal 500 Newton. In the first exercise, you are asked to name and represent, not to a scale, the external forces acting on the bus on the center of gravity of the bus during its motion. Actually, the forces acting on the bus are the weight W, this is the representation of the weight from the center of gravity of the bus, the normal reaction, and this is the representation of this force, the traction force F, and the friction force which opposes the motion of the bus, and this is its representation. Now in the second part, you are asked that by applying Newton's first law, determine the magnitude of the traction force exerted on the bus during its motion. Actually, we have two methods to solve this application. First, according to Newton's first law, the sum of all external forces acting on the bus is equal to 0 vector. Then, W vector plus N vector plus F vector plus F vector is equal to 0 vector. In the first method, as you can notice, along the vertical axis there is no motion, then the sum of the forces acting on the vertical axis is equal to 0 vector, since there is no movement on the vertical axis. On the other hand, on the horizontal axis, W plus N is equal to 0, then we still have F plus F, which is equal to 0 vector, which means that F vector is equal to minus F vector, and in this case, the traction force has a magnitude equal to that of the force of friction, which is equal to 500 Newton. Now in the second method, we project on an axis oriented positively with the direction of motion, in our case along the x-axis, and here is the axis oriented with the direction of motion. Now we project these forces along this axis. Actually, N and W has no components along this axis, so we only have a component for the traction force and for the friction force. Actually, the traction force is applied with the direction of motion, then it has a positive value, whereas the friction force is applied opposite to the direction of motion or to the positive axis, to the orientation of the positive axis, then it has a negative component. So we can say that F minus F is equal to 0, which gives us that F in magnitude, that the magnitude of the traction force is equal to that of the force of friction, which is equal to 500 Newton. Now in the last part, you are asked to determine the distance traveled by the bus during 1 minute. Remember that the bus moves in a uniform rectilinear motion, and in a uniform rectilinear motion, x is equal to vt plus x0, which means that the distance traveled is equal to vt. We have the speed of the bus during its motion, and we have the duration of time, so we can replace them and calculate the value. Don't forget to convert the units. D equal V times delta T. V should be converted into meter per second by dividing by 3.6, and the duration of time should be converted to second by multiplying by 60. Then the final answer is D equal 900 meter. As a summary, inertia is the tendency of an object to resist any change in its state of motion, and the mass is the measure of inertia. Objects tend to keep doing what they were doing unless subjected to unbalanced forces. And Newton's first law states that when an object is subjected to several forces of zero resultant, in other words, balanced forces, it remains at rest if it was initially at rest, or in uniform rectilinear motion if it was initially in motion. This is the end of part 2. Thanks for your attention.